Thank you. Yeah, I feel a bit like an outlier because I'm going to discuss more about software in this talk. So I will give an overview of the Nilearn software and what we can do with that in terms of multivariate analysis. So Nilearn is a Python library that aims at leveraging the power of recent Python machine learning libraries to do some tasks in brain imaging. So for instance, scikit-learn is one of the main Python machine learning libraries. And with this, you can do like encoding and decoding tasks, analyze functional connectivity, and do meta-analysis. So typically with Nilearn, you will write some scripts to analyze your data, and the 4 more steps are first, getting the data, downloading the data. So we have a fetcher to get public data sets very easily, and they support resuming. So if you cannot download all your data in once, you can do it on several times, and it will resume the downloading. Then when you've got your data, you need to put them in shape for machine learning tasks, and for that we have the so-called nifty masker, which is the central tool of the library that gets the images, filters the images, does some smoothing possibly, and then extracts an array of data out from it. So you've got at the end an array where the columns are the features, so the voxels actually of your data set, and the rows are your samples, which can be the time points or the subjects in your analysis. And this kind of shape now is really usable for a machine learning purpose. Then you apply an estimator, so you do some computation, like a classification, for instance, on your data, and you can visualize the results with the library. So you can output images and figures. So in terms of visualization, we propose some tools to plot connectomes, so ROIs and edges between these ROIs, and you can plot the connectivity strengths between these regions. We can also plot probabilistic atlases, so overlapping regions, activation maps. You can add some anatomical features like edges on top of functional images. And more recently, we have added some capabilities for surface rendering, so projections of volumic data to the surface, and then rendering of ROIs on the surface and activation or feature maps on the surface. The main part of Nilearn is to do some machine learning. So decoding is one of these tasks. For this, you need classifiers. So I provide here an example on the AXB dataset, one against all classification scheme, where you can use all the classifiers that you want, those that are available in scikit-learn. So it's typically the tool of choice to benchmark different classifiers. If you want to be sure that you really extracted the information from your data set, you can really have a relatively exhaustive benchmark of existing techniques. But then we have also designed some classification tools more specific to brain imaging, like tools that will not only predict accurately on new images, but also create some structure in the feature map, like having some sparsity and some compact regions, so that you can have a classifier which is interpretable. So it will focus the weight maps into some regions of interest that you can easily state which regions were actually predictive. So this is really very useful for functional neuroimaging. And soon we will also add a new method that has similar features but is even faster and more stable. We can also do some encoding analysis with these classification tools. Here is an example based on the Kamitani neuron dataset, where you can study the mapping between the visual field and the visual cortex. So on the top left, you can see the visual field in red-yellow colors. The colors represent how well pixels in the visual field are predicted by brain activity. And then for a given pixel, the one outlined in blue, you can see the voxels in the map that are predictive of this pixel. Or the other way around in the encoding scheme. So on the figure below, if you look at the right part, you can see for some voxels in the brain how well their activity is predicted by the occurrence of objects in the visual field. So this is color-coded. And then for 4 voxels, we display the pixels in the visual field that explain the activity in these voxels, so the receptive fields of these voxels. So you can run this example with Nilearn. We provide the data and the code. If we shift now to connectivity, one of the tasks in connectivity is to use atlases. First, represent your data with atlases, so you can download standard atlases, but also estimate them from your data. And for this, we provide group ICA, online dictionary learning, and multi-subject dictionary learning techniques. So first of all, if you want a lot of regions, like thousands of regions, you can do that with clustering. It will be more handy. So we provide several tools like k-means, words, linkage clustering. And also soon we will add a super fast clustering called RENA, which is very useful when you want a lot of clusters. But in most studies, you will want a few brain networks, and these you can estimate very easily with online dictionary learning. This has 2 main features. First, it is online, which means that it will upload your data by small chunks. So even on my laptop, I can analyze a data set with tens of subjects. This will fit in memory. And then this delivers some brain maps that are truly sparse. So you don't need to figure out a threshold to isolate the regions. They are isolated by construction. So it's a very useful tool, often more useful than ICA. And then on these regions, you can estimate the connectivity. So we provide tools to estimate correlation, partial correlations, with regularized estimates. So for instance, some graph lasso models that will estimate sparse model of connectivity, or some shrinkage estimates which have good properties, they are very stable and reliable. But the killer feature is the so-called tangent method for connectivity analysis. It's a technique that represents that takes into account the structure of covariance matrices. And so it's a parameterization of connectivity that is well suited to the comparison of different populations. So it was based on theoretical arguments, but we've seen in 5-6 studies now that it systematically outperforms a correlation or partial correlation when we want to compare populations. And we provide examples for that. We can also do some meta-analysis, so image-based meta-analysis by, for instance, downloading the data from NeuroVault, from certain collection of NeuroVaults. You can very easily download the data, look at the images, and then do some summary statistics. So what I show here is just 5 or 6 lines of script. Currently, neuroimaging is shifting towards large scale and large populations, which means that we have to handle big-ish data from lots of individuals, and of course images are large too. And so we need some powerful tool to deal with this size increase in the data. So there are 2 main features that we have implemented in the library for efficiency. Actually, this is based on the joblib Python library. One is parallel computation. It's very simple. You just add an njobs argument to your function, and this will seamlessly run the estimation on the number of processors that you gave. So very useful for if you have some strong machines. And the other mechanism is caching. Very often in a pipeline, you will have to repeat some computation several times because you will reload your data several times, redo the filtering, etc. And if you just provide a memory argument, which is a path toward some place on your disk where you can store the intermediate data, then when the method will detect that you rerun the same thing with the same data several times, and the second time it will not do the computation, but directly reload the result. So it's a big time saver. So if you want to learn from it, you can go to the documentation. It's pretty complete. You will see a lot of examples. So personally, when I have to do something, I just take an example and I just change the path. It's very easy. So you've got IPython notebooks or Python scripts. And here is an example, for instance, of running ICA on a data set. It's literally 8 lines of script. You just need to fetch the data set. So here we've got a fetcher, which makes it pretty easy. You get just the functional data of the ADHD dataset from 30 subjects. And then you run a canonical ICA, so it's a group ICA model, where that you first specify the model, fit it on the data that you downloaded, and get the images, and you can then plot the images. So you've got this in a few minutes and just 10 lines of code. So all this is publicly available. It will be demoed tomorrow in the open science room, 311 at about 2 p.m. I think. This is a code contributed by people from my group, but also from several places like Stanford, Berkeley, Leipzig. So it's really a community development. So don't hesitate to come to make some requests and to contribute. You're welcome. Thank you.